Okay, so welcome to this new class. So in the last class we were determining the limiting conditions to determine the equilibrium diagram of concentration versus partial pressure. So the first condition we took was low pressure of oxygen, that is when oxygen deficiency dominates, that is oxygen vacancies dominate in this particular material. And then charge neutrality, you can establish the charge neutrality condition where oxygen vacancy concentration is half of electron concentration and which is much higher than interstitial concentration, and then you can determine what is the concentration of all the defects, and then I can work out since VO is much greater than OI, I can work out what is the PO2 condition at which this should happen. Okay, so this is first limiting condition. Second limiting condition would be in high pressure region. So in this case opposite prevails, that is oxygen interstitials are much larger in concentration than oxygen vacancies. Again write down the charge neutrality condition and write down derive the concentration of all defects, and then we work out what is the regime of partial pressure of oxygen, which is given in terms of Ks of different reactions. So PO2 must be larger than 16 Kf cube, much larger than 16 Kf cube divided by KOI square. And then the last region which is remaining is the stoichiometric condition. In that case we take two conditions. Case 1, when intrinsic ionization dominates, that is intrinsic creation of electrons and holes. In such a situation the electron and hole concentrations are equal, they are equal to Ki to the power half, and these two concentrations are much larger than oxygen interstitial and oxygen vacancy concentration. So when you determine VO and OI concentrations, then NE is given by this expression. So here as a result oxygen and oxygen vacancy and oxygen interstitial concentrations are vary as P to the minus half, P to the plus half in the intermediate range. Second scenario that we could take was when anti-Frankel defects dominate, that is in that case vacancy of oxygen is equal to vacancy of oxygen interstitial, which is equal to Kf to the power half, and these two are much larger than electron and hole concentration. So we work out from the reduction and oxidation reactions the electron concentration and hole concentration. The only thing you do here is, because VO and OI is now fixed as Kf to the power half, you replace these as values of VO and OI in the expressions which are shown below, and then you can work out what is the concentration of electrons and holes, which goes as P to the minus 1 by 4 or plus 1 by 4. And if we combine all these three regions with the limiting conditions, we get a equilibrium diagram which is called as Brewers diagram. So first one is when internal disorder dominates. So I first draw Ne is equal to NH in the stoichiometric region, then I extend Ne and NH into high and low pressure regions whose expressions are given as the expressions we have worked out, and then accordingly we can also draw OI and VO concentrations. This is OI and VO concentration. So OI concentration we start drawing from high pressure region, because we know that it is equal to half of NH, and then we since the composition has to be continuous, it varies as P to the power plus half in the stoichiometric region, and then again varies as 1 by 6 in the low pressure region. In case of VO, it is equal to half of Ne, and this goes as minus 1 by 6 in the low pressure region, followed by minus 1 by 2 in the stoichiometric region, followed by minus 1 by 6 of PO2 to the power of PO to the power of minus 1 by 6 as in the high pressure region. So this is the diagram that you get when you when you assume that internal disorder dominates in the material. On the contrary, if you have anti-Frankel disorder which dominates in the intermediate PO2 range, then the stoichiometric composition, stoichiometric state is, or intermediate pressure state is governed by OI is equal to VO, and then you extend OI and VO into high and low pressure regions according to the expressions that we worked out previously. And then since we know Ne is equal to 2 of VO, NH is equal to 2 of OI, we draw the lines for both Ne and NH as per the slopes that are obtained in each of these regimes. So these are two equilibrium diagrams that we developed, and these are very easy now. As you can see, they look complicated, but they are much more easier to derive if you know the fundamentals well, if you write the defect reactions properly. And we also, and choice of internal anti-Frankel or Schottky defects or whatever the kind of defects which prevails in the intermediate PO2 range, usually those defects are the defects which prevail in the low or high pressure regime. So, your intermediate, so for example, if an oxide is prone to having Schottky defect, in that case the intermediate pressure intermediate PO2 range would be VO is equal to Vm. So, the defects that would dominate in the low and high pressure regime would be either VO or Vm. So, you do not have OI or Mi. So, that is how it would change. Or if you had Frenkel disorder dominating, then you would have Vm and Mi. So, the kind of defects which are going to dominate in each of these regimes are governed to a large extent governed by what is the situation in the intermediate PO2 range, and that makes our life much more easier. So, as you can see, if you write the defect reactions properly, if you work out the limiting conditions, then you can work out what is the diagram, Brewers diagram for which is nothing but log of concentration versus log of PO2. And the top part of this, if you look at the top part of this diagram, for example, if I, and this was the exercise which I gave you, which hope you follow, and then top part of this diagram would go as, if you, so basically no matter what, the top part of the diagram would look like this. So, when you make, now top part of the diagram is basically the majority concentration. So, this is regime 1, regime 2, regime 3. So, let us say in this regime you have VO, in this regime you have OI, in this regime OI is equal to VO. Okay. So, when you make conductivity measurements in, so this is PO2 on log scale and this is concentration. So, when you make conductivity measurements, so now if I make conductivity measurements, then conductivity measurements would scale as similar manner. So, from the conductivity measurements you can work out what the defect scenario in each of these materials is going to be, which makes life relatively easier, because and in this of course the temperature is constant. All these measurements are done at constant temperature. So, I hope the situation is clear now with respect to defect equilibria. Now, what we will do is that we will look at the comparative performance of couple of oxides versus oxygen pressure. What happens in two different materials, let us say at different oxygen partial pressures. So, this is here, this is so what we will do is that comparison of two oxides. Okay. So, we will take MgO and TiO2. So, first we will take the case of MgO. Okay. Now, MgO, if it is pure form, then intrinsic defects are, as we know, we have talked about Schottky defects. So, MgO is prone to, most of the closed packed materials are prone to having Schottky defects, which means Vmg and VO. These are two dominating defects. Okay. So, what would be the defect reaction under oxidizing conditions? So, under oxidizing conditions you will have oxygen coming into the system and this would go to oxygen site. Now, you have created one oxygen site, compensate for that you will have one magnesium site which would be vacant, and that will give rise to two holes. So, this would be the defect reaction, and K for such a reaction would be K ox, let us say this would be Vmg multiplied by NH square divided by PO to the power half if OO was equal to 1, if I take a dilute solution. Now, K experimental value for this reaction is 7.2 into 10 to the power 63 to exponential of minus of 610 plus minus roughly 10%, 680 divided by RT, and this is kilojoule per mole. Okay, this is the experimental value of K, and the units are centimeter to the power minus 9, MPa to the power minus half. Okay. Now, you can see from this expression that what happens as you increase the temperature. Now, as you increase the temperature, since this is minus sign is here, the K value also increases. As a result, what it means is that MgO can be oxidized at higher temperatures, which means producing more and more intrinsic magnesium vacancies and holes if no other defects were present, if no other extrinsic defects were present. So, from the electrical neutrality condition, you can write electrical neutrality condition gives you NH is equal to 2 of Vmg. Okay. So, let us take two examples of different temperatures. So, let us, I mean, even though in reality, even though the concentrations are very small, but they still vary as a function of partial pressure of oxygen as well as temperature. So, for example, we take melting point of Tm of MgO is about 2480 Kelvin. So, let us say T is equal to 0.8 of Tm, okay, and atmosphere is air, which means 0.21, PO2 is equal to 0.21 atmosphere. Under these conditions, Vmg can be worked out as so, you know what the temperature is. I can just put the value of temperature here to get the value of K, and I know from the previous slide that K is equal to Vmg NH square by Pa to the power half. So, I replace NH is equal to 2 Vmg, which means this whole expression becomes 4 Vmg cube. So, 4 Vmg cube will be equal to Po to the power half multiplied by Kox, and Kox is experimentally determined as a function of temperature. So, when you make these substitutions, so Vmg would be your, so I write 4 Vmg cube is equal to Kox multiplied by Po to the power half, which means Vmg is equal to 1 by 4 to the power 1 by 3 into Kox to the power 1 by 3 Po to the power 1 by 6. So, I can determine Kox from this expression as a function of temperature, and I know PO2 is equal to 0.21 atmosphere. So, if I make appropriate substitutions, then what I get is Vmg is equal to 2 into roughly 10 to the power 16 per centimeter cube, and this works out to about 0.6 ppm in Mg1 minus XO. So, this X would be 0.6 ppm, okay, because magnesium deficient would mean Mg1 minus X. X is the level of deficiency, and level of deficiency is equivalent to vacancy of magnesium, and this works out to around 0.6 ppm. Now, if you change the partial pressure of oxygen, so if you take PO2 is equal to if you take PO2 to be equal to 10 to the power minus 9 MPa, in such a situation again you recalculate, and this gives to Vmg concentration of about 2 into 10 to the power 15 centimeter per centimeter cube. This is equivalent to 0.04 ppm in Mg1 minus XO. So, if you compare these two values, in previous case we got 0.6 ppm, and now we have got 0.04 ppm. So, by reducing the partial pressure of oxygen by about 9 orders of magnitude, we get only a difference of an order of magnitude in the magnesium vacancy concentration. So this is about magnesium oxide. So here we see that when you change the pressure, for example, at a fixed temperature of 0.8 of melting point, you do not see an appreciable change in the concentration of magnesium vacancies. On the other hand, if you take example of TiO2, now TiO2 is also an oxygen deficient oxide, so it is very prone to non-stoichiometry. So in this case, this is let us say, let's modify a little bit, TiO2 minus X. So this is going to have oxygen deficiency. In case of MgO, we looked at magnesium deficiency, and here we look at oxygen deficiency. So the reaction is of course the reduction reaction. So 2OO plus Ti at Ti site, they go to Ti interstitial plus O2. So since oxygen has gone out, the titanium site is also lost and it has become an interstitial, and this gives rise to 4 electrons. Okay. So the electrical neutrality condition we know is equal to Ne is equal to 4 of Ti, assuming that titanium interstitials are so, and Kr would be Tii multiplied by Ne4 into PO2, and if you make this to be equal to, so this becomes 256 Ti I to the power 5 multiplied by PO2. Okay. So Ti I concentration becomes Kr divided by 256 to the power 1 by 5 into PO to the power minus 1 by 5. Let me have a just look. Yes, minus 1 by 5. So this would be your Ti concentration. Now I know that Kr experimentally is determined as 6.55 multiplied by 10 to the power 22 into exponential of minus 960 kilojoule per mole divided by RT, and this has a unit of MPa centimeter inverse. So now again I take T is equal to 0.8 of Tm, and which is nothing but about 1690 Kelvin in titanium oxide. So I work out, so if you put the value, this value of temperature, you can work out what is T, what is Kr, and PO2, let us say, so let us say in air PO2 is 0.21 atmosphere. So if you work out Ti now, so make sure you put the right units in every place, because units are very important, and what you get here is 1.4 into 10 to the power 18 per centimeter cube. So first of all, if you compare the magnitude with respect to magnesium, in case of magnesium we got around 10 to the power 16 per centimeter cube at atmospheric pressure, and here you have 2 orders of magnitude high. So even at atmospheric pressure at the same temperature, that is 0.8 of melting point, titanium oxide has much more 2 orders of magnitude higher defect concentration in comparison to MgO, and this works out to roughly 93 ppm in TiO2 minus X. So this X is 93 ppm. Now if you take PO2 is roughly 10 to the power minus 9 megapascal, same pressure as in case of MgO, and again at 0.8 of Tm, then you work out what is K. K experimental will give you the value of K at 0.8 . and then you know what is Ti expression. So, Tii would be under such condition is 4.18 into 10 power 19 per centimeter cube. So, you have seen that although the relative change in the magnitude at two pressures is only about 1 order of magnitude, but this is equivalent to roughly 0.27% in TiO2 minus X. So, this X is 0.27%, it is a significantly large number. So, because of this because of this large change, large difference in the defect concentrations of two oxides that we have taken, TiO2 makes a excellent n-type conductor, but MgO does not. So, if you want to make MgO conducting, you need to put impurities, that is, you need to work through extrinsic defects, and that we have seen earlier what happens when you put defects in MgO. So, this I hope clarifies some of the basics related to ionic defects. Now, we will look at some of the fundamental things related to electronic disorder in the material. We have talked in very brief about electronic disorder just by writing a defect reaction. Okay. Now, unlike intrinsic point defects, which are your vacancies or interstitials, or electronic defects are typically created by either thermal means or optical means, which means what happens in these materials is basically you have two types of materials. One is semiconductor and insulators, and oxides typically form in any of these two categories, and they are different from the metals in such a sense that they have a forbidden energy gap. So, this is your energy gap in the energy band diagram, and this is Eg, which means nothing exists. So, this separates basically your valence band and this is your conduction band. So, this valence band is typically at 0 K would be filled, and this would be empty. Okay. So, any conduction which has to take place in these materials having a particular band gap. So, this Eg value of Eg would be about typically below 2.5 electron volt for semiconductors and greater than 2.53 electron volt for insulators. So, any if these guys have to conduct any electricity or any charge conduction has to take place, the electrons from the valence band, which is here, they have to be excited across this energy gap to go there, and as a result it gives rise to a hole. Now, this process, which means the process which has to occur here, it can be thermal process or an optical process, because you need to supply an energy which is at least equal to or higher than Eg. So, that is where so that is why these defects are a little bit different in terms of so basically you can consider this energy band gap as an energy which is equivalent to your defect formation energy in terms of intrinsic point defects. In terms of intrinsic point defects, if you look at the statistical model, then in order to create certain number of defects, you need to overcome the energy barrier of defect formation energy, that is delta HF. Now, here you need to overcome Eg in order to create electron hole pair or to create electronic disorder or electronic defects. So, defect density as a result is nothing but number of electrons or holes in the material, and you can express in terms of per centimeter cube. And another thing that is of interest in these materials is something called as Fermi energy, and this Fermi energy for intrinsic semiconductors sits at the middle of the band gap, and once the semiconductor or insulator starts becoming extrinsic, which means you start putting in defect, then this Fermi level moves up or down. So, if you make it n type, the Fermi level will move up for n type, and for for p type it will move closer to balanced wind. And when you start putting in impurities, then you also introduce something called as donor or acceptor levels. So this would be your acceptor level, which means it will accept electrons from the valence band, giving rise to large hole density in the valence band, and this will donate its extra electrons. So this is typically, for example, in silicon, if you take in silicon, your aluminum would be an acceptor, because aluminum is +3 atom. So it would attract an it will receive an electron from the valence band, creating a hole in the valence band. So this is an acceptor level, which, and this difference in the energy is very small. It's of the order of few milli electron volts, which can easily happen at room temperature. Similarly, this level will be called as donor level. So I can write this as ED, I can write this as EA, and again this energy difference EC minus ED is very small, is of the order of few milli electrons volts. So that all the excess electrons from donors, for example P5 plus phosphorus, so electrons from the donor impurities can be excited into the conduction band without spending any extra energy at room temperature, and this gives rise to large density of conduction electrons in the conduction band. So, and the Fermi energy is an energy, so you know what Fermi energy is. So when you plot, for example, so this is, let us say, EF, this is E versus so this is from the Fermi-Dirac statistics, which means all the energy at 0 K, all the energy levels below Fermi energy, so and Fe would represent the probability of occupation. So what it basically tells you is that all the energy levels below EF are filled at 0 K, and nothing above EF is filled. So this is your 0. So this is at 0 K. And as you increase the temperature, so at a finite temperature, this will go through half. So this would be your half point. So number of electrons, so the number of electrons from the levels just close to Fermi energy will leave and go into the adjoining bands. So this would be your definition of Fermi energy. So typically for an intrinsic semiconductor, it sits right in the middle of the band gap. Some of the band gap values, for example, in case of semiconductors, your silicon has about 1.1 electron volt, germanium has 0.7 electron volt, and in case of oxides, for example, zinc oxide has about 3.2 electron volt, magnesium oxide has 7.8 electron volt, nickel oxide has roughly 4.2 electron volt, iron oxide is close to 2 something electron volt, close to 2 electron volts. Your Fe2O3 has about 3.1 electron volt, barium titanate, a very important material for many practical applications, is about 2.8 electron volt, and so on and so forth. Silicon oxide, for example, has large band gap of 8.5 electron volt, TiO2 has 3 electron volt, and you can find many more values in the literature. So these are some of the band gap values. So typically higher the band gap is, less conducting the material is in the intrinsic state, okay, unless you create defects from some other means. So the defect concentration, since we know that it depends upon, since we know that you have to provide enough energy, which is a thermal energy thermal or optical energy in order to overcome the energy barrier, it can be written in terms of probability of electrons or electrons crossing this gap. So so concentration of electrons or holes are equal in an intrinsic. So Ne is equal to NH in an intrinsic solid, and this is given as Ne is equal to Nc exponential of minus of EC minus EF divided by KT, and you know what EC and EF is. So, this is your EC, conduction band edge, the bottom of conduction band, and EV is top of valence band. Okay. So, NC, where NC is the effective conduction band density of states. Density of states, and similarly NH is given as NV into exponential of minus of EF minus EV divided by KT. So, basically you can see that now for an intrinsic semiconductor, EC minus EF would be equal to, for an intrinsic semiconductor, EC minus EF is equal to EF minus EV is equal to half of EG, because it sits right in the middle. So, you can see that this would change to minus of EG by 2 KT, and this would also change to minus of EG by 2 KT. And you can see, as so if that is the case, then as EG increases, what would happen to NE and NH? Both NE and NH would decrease, and also as temperature increases, both NE and NH would increase. And this NV, I forgot to mention, would be effective conduction slash valence band density of states, depending upon which case you are referring to. And NC and NV values are given as NC is equal to 2 into 2 pi ME star KT divided by H square and to the power 3 by 2, and NV is equal to 2 into 2 pi MH star KT divided by H square to the power 3 by 2, and ME star and MH star are effective mass of electron, and this is effective mass of hole, and K is Boltzmann constant, H is Planck's constant, and that you can. So, at about 300 K, which is roughly room temperature, NC is equal to NV is roughly 10 to the power 19 per centimeter cube, if ME star was equal to MH star. Okay. Which means mass of free electron, effective mass of free electron is equal to effective mass of hole. Now, that is not necessarily a true condition, but just for the sake of doing it, we know that Ne is equal to NH. For an intrinsic semiconductor, I can write EF to be equal to EC plus. So, if you make Ne and NH equal to, what it becomes is that EC plus EV by 2 plus 3 by 4 KT ln MH star divided by ME star, and this EC plus EV by 2 is nothing but EG by 2. So, this becomes so your EF becomes EG by 2 plus 3 by 4 KT ln MH star divided by ME star. So, if this was equal to 1, then EF was equal to EG by 2 for an intrinsic semiconductor. This is what we assumed to begin with. So, but typically in oxides, your effective masses are about 2 to 10 times of Me or effective mass of free electron, let us say Me naught, which is the free electron mass. Okay. And You know that atomic density of solids is roughly 10 to the power 23 per centimeter cube. So, density of states is about 4 to 5 orders of magnitude lower than in semiconductors. So, this gives you an idea about the density of states value in the oxides. Now, if Me and Mh were equal, then you can write Ne to be equal to Nh to be equal to Nc Nv to the power half into exponential minus Eg by 2 kT. Okay. Now, this expression is very similar to what you see for defect concentration. For defects, we worked out N by N is equal to exponential minus delta Hf by kT 2 kT, right. So, in case of Frenkel defects, so you can see the relation here. You need to overcome energy of delta Hf in order to create the defects. Here you need to create overcome an energy of Eg in order to create electronic defects. So, it's very similar. These expressions are very similar because the fundamental concepts are similar. You need certain energy in order to overcome an energy barrier to create the defects. Okay. So, density of electronic states in a material can be thought of as equivalent to density of vacancies in the lattice sites. So, expressions are equivalent, that is why you can make them equivalent. And the depiction in terms of chemical reaction, if you want to, in terms of so reaction, of course, as we saw, was electrons plus holes, and this was, for this reaction constant would be Ne multiplied by Nh, which is equal to Nc into Nv into exponential minus Eg by kT at about 300 K, and this Ki is approximately 10 raised to the power 38 because this is 10 to the power 19. So, this will be 10 raised to the power 38 exponential of per centimeter cube. So, this would be 10 to the power 38 exponential minus Eg by kT, and this would be 10 to the power minus 6. So, this is how you can determine what would be the values of Ki for intrinsic ionization. So, now so in summary, basically what we have seen is for electronic disorder that the oxides typically have ionic solids or semiconductors, covalently bonded solids, they have an energy gap. In order to create electron and holes, you need to overcome an energy which is nothing but the band gap, and depending upon how much energy you provide, you will create a certain electron or hole concentration, and this equation is pretty much similar to the vacancy concentration or Frenkel defect concentration that we worked out in case of equilibrium defect concentration. So, concepts are similar except that the type of energies are different. So, now we will move on to some of the examples, and for example, we will take what is the we will take the case of MgO, and we will see what is the intrinsic electronic and ionic defect concentration. So, what we will see is that, because the point here is just to see which one dominates, and we will see later on that which one is more likely to be present in that particular environment. So, this is an example. Okay. So, consider, so MgO as we know has Schottky defects, and the defect formation energy delta Hs is about 7.7 electron volt. Since they have Schottky defects, it is 7.7 electron volt, and the band gap Eg is about 7.7 what we saw earlier, is about 7.8 electron volt, and this band gap changes as you increase temperature of MgO. So, this minus of so basically your band gap is going to decrease as you increase the temperature. Okay. So, the question is, now in a completely pure and stoichiometric magnesium oxide, which defects are likely to be created, and or which defects are going to dominate, is it ionic or electronic? So, let us say temperature. So, let us say temperature is equal to about 1400 degrees centigrade, and that is 1673 Kelvin. So, we can write the defect. So, intrinsic defects are VO and Vmg. So, concentration of VO is equal to concentration of Vmg, and this is equal to nothing but your Ks. This is a Schottky defect reaction to the power half, and this is nothing but equal to exponential of we are taking it in this in mole fraction. So, exponential of minus delta Hs by 2 kT, and if you put in the value of delta Hs and at this temperature, this comes out to about 2.5 multiplied by 10 to the power minus 12 mole fraction. Okay. Now, how do you calculate the electron and hole concentration? Just use the formalism that we have used earlier. So, we know that Ne is equal to Nh is equal to Ki to the power half, which is equal to Nc Nv to the power half into exponential minus Eg by 2 kT, right, and this would be given as 2 into kT to the power 2 pi h square into Me star into Mh star to the power 3 by 4 to exponential minus Eg by 2 kT. So, what I have done is, if you go to previous slides, Nc and Nv were equal to, yeah. So, what I have done is basically replace the value of Nc and Nv in those expressions. So, this is how it becomes, and in MgO we know that Me star is equal to 0.38 of M naught or Me naught, and Mh star is equal to 0.77 Me naught. Typically, effective mass of hole is much more higher as compared to effective mass of electron, and what we find is an Me naught is equal to nothing but this particular thing is 9.1 into 10 to the minus 31 kg. So, at the temperature of interest, which is at 1673 Kelvin, you know that the band gap also changes. So, you need to work out what is the Eg. So, Eg will be equal to 7 point, how much was it? So, we have taken 7.8 minus the difference of 1673 with respect to, so that value was given as at, so basically delta T at 1673 minus room temperature multiplied by d by dt. Okay, and this would come out to approximately 6.2 electron volt, and this would give you Ne is equal to Nh is equal to, if you replace the value of temperature here, take the Boltzmann constant, take the Planck's constant, Me and MH naught, we know what is Eg, and if you do that, you get about 4 into 10 to the power 10 per centimeter cube. So, now if you compare these two concentrations, here it is 4 into 10 to the power 10 centimeter cube, and in the previous case it was 10 to the power minus 12 mole fraction. So, the question now here is how to convert it to per centimeter cube. So, Vmg conversion into per centimeter cube. So, basically 2 into 10 to the power minus 12 mole fraction multiplied by, you will have to multiply it by density of MgO in grams per cc multiplied by Na, which is Avogadro number, which is number per mole, and this has to be divided by molecular weight of MgO, which is gram per mole. So, if you do that, this is 2.5 into 10 to the power minus 12 multiplied by density is 3.58 multiplied by Na 6.023 into 10 to the power 23 divided by molecular weight of MgO is about 40.3, and this would come out to around 1.4 into 10 to the power 11 per centimeter cube. So, if you compare these two magnitudes, now here you get 4 into 10 to the power 10 and here you get 1.4 into 10 to the power 11. So, at 1400 degrees centigrade, if you compare these two energies, now if you look at the previous energies, the energy at that particular temperature, the defect formation energy 7.7 electron volt and the band gap is about 6.2 electron volt. So, there is a difference of 1.5 electron volt, but still the defect concentration in MgO is Schottky defects concentration is much larger, is an order of magnitude about larger as compared to electronic concentration. So, you can see that at a particular given temperature which defects will dominate using this kind of analysis. So, another thing that you would like to see is the role of impurities, role of donors or acceptors. Now, when I make a band gap like this is your EC, this is your EV. I said that in a semiconductor, when you put an impurity, so an impurity which let us say A you put, and if it becomes, so A star, let us say A or B, so A dot, and it goes to let us say M site, and if you put B, B goes to M site. If it gets reduced, it gives rise to a hole. Okay. So, this kind of impurity will be a donor impurity, and this kind of impurity would be an acceptor impurity because it creates an hole. So, typically the acceptor level is very close to, as I just explained in the previous slide, this is your EA and this is your ED, and the EV minus ED or EA minus EC are equivalent to or smaller than KT. So, basically of the order of few MEVs in a typical semiconductor. Okay. Now, in case of, for example, in case of oxides, if you form oxygen vacancies, for example, OO goes out, it gives rise to half O2 which goes out, gives rise to oxygen vacancy, gives rise to 2 electrons. So, here formation of oxygen vacancy has given rise to 2 electrons, which means oxygen vacancy acts as a donor impurity. So, this would be in an oxide, for example, oxygen vacancy, and acceptor would be your, for example, metal vacancy. So, if you have if you have this reaction, then this would be metal vacancy. Similarly, your oxygen interstitial would go at this site. So, acceptor levels would be typically metal vacancies and or cation vacancies, anion interstitials, and donor level would be your anion vacancy and cation interstitials. The difference in energy would depend upon the fact that how much, what is the level of ionization of these impurities or these defects, whether they are singly ionized, completely ionized or neutral, and this would determine their basically level of typically what you will find is that that as the ionization increases, the energy also the difference in the energy also increases. So, although we have taken most of the cases in our module as completely charged impurities, the defects or impurities may not be completely ionized. In case of impurity, if you take for example in MgO, aluminum, if you are putting aluminum, then aluminum goes to magnesium site, this would be positively charged. So, donor, and if you put sodium at magnesium site, this would be negatively charged, giving rise to a hole. So, this would be acceptor. Now, depending upon type of defects are created, level of their ionization, these energies, the difference that the donor and an acceptor, the distance of donor and acceptor levels with respect to conduction and valence band edge would change. So, for instance, in case of MgO, so this is your EC, this is your EV in case of MgO. So, if your Vmg dash is about 1.5 electron volt. So, this is EA, and this is your VO ED, and this is about 2 electron volts, and you know that in case of MgO the band gap is about roughly, let us say 8 electron volt, is about 7.8 or 7.9 electron volt, and depends on the temperature as well. So, this would be your Eg minus Ed plus Eg minus Ed minus Ea. And here we are talking of, so if you talk about VOX, then this would be much more smaller, about half electron volt. If you take singly ionized magnesium vacancy, this would be roughly 0.5 electron volt. So, depending on the level of ionization, the difference in the energy levels would change, and similarly if you put aluminum and sodium, they would also introduce their energy levels respectively at various places. So, finally, we will just come to final topic now, and final topic is just to consider electronic and ionic compensation of solutes. So, for example, you take the which one is more preferable. So, example we take of ionic versus electronic compensation. So, example we take is Nb2O5 doping in TiO2. Okay. So, what is the defect reaction? The ionic defect reaction would be, so ionic defect reaction means no electronic defects are created. So, which means something is going to happen at cation site. So, you put 2 Nb2O5, I am going to write balanced defect reaction. So, all those 4 niobiums go to titanium site, which means niobium is plus 5, titanium is plus 4. So, it is going to carry 1 positive charge, plus all the oxygens go to oxygen site. So, now there is a problem here, since all the 10 oxygen go to oxygen sites, but only 4 niobiums go to titanium site, whereas stoichiometry requires 1 cation site for 2 anion sites, which means I create a vacancy of titanium, which would be 4 charged, minus 4 charged. So, this would be the site balance. So, in order to compensate for 2 extra oxygens which are coming as a result of Nb2O5, you need to create 1 extra vacancy of titanium. So, this is a ionic defect reaction. Now, electronic compensation. So, I can again write 2 Nb2O5, again all the 4 niobiums are going to titanium sites. Oops, so mistake here, plus 8 OOX plus O2, which means for 4 titanium sites I take in only 8 oxygens, rest of the oxygens go out, but now I have to balance the charge. So, which means I have to create 4 electrons. So, this is so let us say this is reaction 1 and this is reaction 2. So, if I now subtract the reaction 2 from reaction 1, then what I get is Nb2 Nb2O5 cancel each other and NbTi will cancel each other. What I will have is O2 plus 4E. So, 1 minus 2 gives rise to O2 plus 4E 2OOX plus VTi. So, what this tells you is that as you increase the partial pressure of oxygen, the reaction will move into forward direction, which means at higher partial pressure of oxygen, your formation of titanium vacancies is going to be preferred. Similarly, if you have lower pressure of oxygens, the reaction will push into the backward reaction, which means electronic compensation is going to be favored at. So, high PO2, you have ionic compensation, this is obvious from this reaction, and low PO2 will give rise to electronic compensation. So, this is pretty clear from this reaction. Now, similarly, as you increase the temperature, as you decrease the temperature, oxidation is again favored. So, temperature increases means oxidation increases. So, as you increase the oxidation, then again formation of titanium vacancies is favored. So, you basically put in the more oxygen into the system. So, as now we can see, so NB basically, so you can create conditions like if Nb2O5 concentration is large, PO2 is high and temperature is low, all these conditions prefer ionic compensation, and converse is true in case of electronic compensation. In any case, you have to follow the electrical neutrality condition. The electrical neutrality condition would be NVTi 4 VTi plus hang on just a second, let me just see what the reactions are. So, I have here NBTi is equal to electron, VTi is equal to 4 of NBTi. So, NBTi is equal to 4 of VTi, right. So, I will have, so NBTi will be equal to 4 of BTi plus Ne, because you have 4 times. So, in case of ionic composition, it is 4 times the vacancy concentration. In case of electronic composition, it is equal. Okay. And similar effects you can see in oxides such as barium titanate, etc. I can give you a home question to work out. For example, you can do the same exercise for material like titanium oxide. So, homework can be do the same for TiO2, and for this you can refer the books which I have subscribed in the bibliography related to Similarly, same is true about calcium oxide doping in zirconium oxide. Again, you can have electronic compensation or the ionic compensation. So I will leave it to you to work out the defect reactions. What happens when you dope zirconia with calcia or yttria? By this time you should be pretty much familiar with how the defect reactions are written. And the one thing which I want to point out is that when you put all these dopants, for example, into the host lattice, they give rise to a change in the volume. So, for example, when you dope zirconium oxide, so CaO in ZrO2, so the density of these materials also changes, so at appreciable large concentration. So, when you put, if cation interstitials are present, it is like this, but if anion vacancy is present, so depending upon what kind of defect you have, you will have difference in the level of reduction, but the volume changes are observed, and as a result you have volume or mass changes, you can say. As a result, you have changes in the density. So, basically density is the parameter which takes mass and volume both into account. So, level of type of defect would decide the change, magnitude of change, but you have a change in the density when you start doping the material. If you want to go into details of these things, you should go to the case studies given in the books, but as you can understand. So, what we have discussed in this module is basically we have taken the defect equilibria. First of all, we started with the defect, how the defects are formed, what are the various defect reactions, how we can treat these defect reactions as chemical reactions, the basis for that, and then and we also worked out how the equilibrium concentration of defects is calculated, what happens when you put impurities inside a particular material, and then we looked at the conditions, the concentrations of defects at various partial pressures of oxygen by creating the limiting conditions in high and low pressure range and created an equilibrium diagram. And finally, we took some case studies just to see what kind of defects dominate in which kind of material. So, I hope this gives you a fair idea about the second module, which would be instrumental in going to the third module, which is about now more applied, in the sense that now we know about the defects, what sort of defects are going to form. What we will see in the next module is how these defects move and what sort of properties they give rise in ionic solids. Thank you.